NDI is a transport protocol at its core, not tied to any specific codec, meaning it can carry all kinds of media formats, compressed or uncompressed, depending on what the workflow needs and what the devices support. This flexibility makes it great for balancing image quality, network load, and latency. Let's first of all take a look at NDI high bandwidth, also known as full NDI. In most professional setups, NDI uses its own intra-frame codec based on Speed HQ, which was developed specifically for real-time production. It's designed to give you high image quality with ultra-low latency, and it supports 8-bit and 10-bit video, 422 chroma subsampling, and an embedded alpha channel for transparency, as well as HDR video. Because each frame is compressed individually, there's no delay caused by inter-frame dependencies, and that keeps latency low, under 1 frame as it happens. And that makes the stream robust against packet loss, perfect for switching, mixing, or editing live. Roughly speaking, the bandwidth needs are around 125 megabits per second for 1080p 60 and around 250 to 300 megabits per second for 4K P60. NDI HX, well, that's a more network-friendly version of NDI. It's meant for devices with limited bandwidth, such as IP cameras, wireless links, or mobile equipment. Depending on the hardware, it uses standard video codecs like H.264 or H.265 and offers 8-bit and 10-bit support, 420 chroma subsampling with optional alpha, as well as HDR support. It also provides much lower bandwidth, typically 5 to 20 megabits per second, and is fully compatible with the rest of the NDI ecosystems. Receivers automatically adapt to the stream. NDI HX3, well, that's the newest version of HX and a big step forward. Unlike earlier HX versions, HX3 has clearly defined compression, latency, and GOP structure specs, making it much more predictable and reliable for production use. Key points here are that it uses H.264 or H.265. Again, it supports 8-bit and 10-bit color. 420 chroma subsampling is applied with embedded alpha channel, and it's HDR ready. And it has a fixed GOP size of 20 frames and latency under 100 milliseconds glass to glass. It runs at the bit rates of 1080p 60, around 50 megabits per second for H.265, 4K P60, well, that's around 84 megabits per second at H.265. In short, HX3 provides really high quality video at lower bandwidth without compromising on latency or reliability. NDI wasn't just made for video, of course. It's also a powerful tool for real-time audio over IP, handling multiple audio formats, supporting high channel counts, and keeping everything in sync with video without needing external timing protocols. Audio formats supported are PCM, uncompressed, 48 kilohertz, and 32-bit float. It supports unlimited channels as well. It also supports AAC, which is compressed audio up to 2 channels, and Opus compressed up to 255 channels. All audio is carried together with the video in a single stream, so there's no need for additional sync mechanisms like PTP or Precision Timing Protocol. This design keeps audio and video really tightly aligned, and it's great for live production. Internally, NDI always converts incoming audio to a consistent 32-bit float format to ensure precision and compatibility. And where NDI audio really shines is in live streaming and broadcast and remote production with the use of NDI Bridge. Also in webinars and online training, PA systems and Wi-Fi audio, home entertainment and wireless audio. And the tools and the ecosystem which use NDI audio are NDI Virtual Sound Card, which is software audio input-output over NDI, and NDI Audio Direct VST3 plugins for DAW and real-time integration. NDI Audio also lets you use the same infrastructure for video, audio, and metadata, making workflows more straightforward and flexible. It's not here to replace precision audio over IP systems in every case, but it's certainly more than enough for most production scenarios. One of the lesser known but most powerful features of the NDI protocol is its native support for metadata. Now, this capability enables devices and software to exchange structured information alongside video and audio, opening the door to remote control, automation, broadcast signaling, camera settings exchange, and many more applications. So why does metadata matter in NDI? Well, NDI embeds metadata directly into its transport stream using UTF-8 XML, a flexible and extensible format. Now, this enables real-time control, for example, camera iris and tally light and PTZ position, a transmission of auxiliary data like captions and subtitles and LUTs, etc. An integration with broadcast standards like SCT or SIMPT. Custom data exchange also happens between systems, for example, like device IDs, scene names, tracking info, and so on. And this design is really efficient. Not only that, it's backward compatible and forward compatible. Unrecognized metadata is ignored, ensuring that smooth communication between devices happens even when new features are added. There is a need for standardization because until now, metadata usage in NDI has been mostly ad hoc. Different vendors have implemented their XML schemes, often without clear documentation or guaranteed interoperability. A new initiative proposes a structured framework for third-party metadata standardization within the NDI ecosystem to address this. And the goal is to promote consistency across devices and applications and ensure interoperability and future-proofing, making metadata integration transparent, documented, and maintainable. Creating a platform for third-party contributions is important because this effort includes the development of a public web portal where developers, manufacturers, and integrators can register and submit new metadata formats. They can provide usage examples and XML schemes and undergo a review and approval process. They can also publish approved formats as part of the NDI standard. By formalizing this process, the whole NDI ecosystem opens up to collaborative development to ensure that innovations in metadata like camera control protocols or subtitle formats can be shared and reused by the entire community. In a typical NDI workflow, the receiver selects which transmitter and stream to connect to, establishing a direct connection between the two devices. This is the most common and flexible way NDI works. But there's another approach, because some software applications simulate a traditional video router, like the ones you'd find in an SDI environment, for example. These NDI routers will act as virtual sources, allowing you to manage switching in a centralized manner without physically routing any video whatsoever. A basic version of this is already available in NDI tools as NDI router. So how does it work? Well, although the routing software appears on the network as a source, it doesn't send video itself. The video stream still flows directly from the original NDI transmitter to the final receiver. What the router does is simulate an NDI source, and when you switch inputs, it tells all connected receivers to start pulling video from a different real source. So behind the scenes, why does it matter? Well, the video never passes through the router machine. Switching is instant and seamless, and there's no CPU or GPU or network load for video processing on the router itself. Centralized switching logic is important because it distributes video delivery. You get the flexibility of receiver-based switching with centralized control, just like a traditional router, but entirely in software. Behind every NDI stream, whether it's a PC running a production software or a tiny embedded camera, there's something quietly working in the background: the NDI configuration file. So what does it do? Well, it defines how your NDI device discovers others. It controls visibility and group membership, and it sets stream names, enables or disables multicast, and specifies manual connections across networks. So where is it, this configuration file? Well, on Windows or Mac OS, it's managed via the Access Manager, the NDI Access Manager, and on embedded Linux, it's edited manually. And examples of what you configure are discovery method, NDNS or discovery server, group membership, send and receive visibility zones, or manual source entries, IP-based for firewalls or VPNs. It can also help with multicast enablement for large-scale distribution and stream name overriding to give friendly names for source lists. Once you understand this file, well, then you can deploy and manage NDI reliably, really across any environment. In small NDI setups, everything just works. But as networks scale, controlling visibility becomes essential, and that's where NDI groups come in. NDI groups mean that a sender can be in one or more groups and a receiver can discover from one or more groups. If they don't share a group, well, then they won't see each other. Groups can be used to isolate productions or departments and prevent accidental cross connections. They can be used to organize sources in multi-studio or campus deployments and limit visibility to protect unicast transmitters from overload. And they can be configured in NDI Access Manager for Windows or Mac OS. Just simply use the Groups tab and define send groups and receive groups. They can also be configured manually via the config file in a Linux environment, for example, using JSON commands like this. Remember, groups affect visibility, not security. And discovery filtering happens at the receiver, where the group string must not exceed 248 bytes. In short, groups are really simple but really powerful, and they're perfect for structured scaling. NDI transmitters and receivers don't require synchronization to function. NDI can run sync-free, which simplifies deployment and reduces costs. However, some scenarios do benefit from frame-level alignment, especially in software workflows. Physical devices, such as cameras, well, they synchronize via Genlock using Blackburst or similar methods, whereas software-only devices, like renderers, well, they use system clock syncs like NTP or PTP, but frame timing can still vary. NDI Genlock solves this because it synchronizes a software application to any visible NDI source. And it works over LAN, WAN or cloud and supports cross-frame rate locking if necessary, although that's not recommended. It also can fall back to system clock if the source can't be locked. To use NDI Genlock, well, you'll need to use NDI version 5 or newer for best results, and make sure that there is adequate bandwidth, which multicast can really help with. You'll also need to avoid irregular sources, for example, test pattern tools, when using it. NDI Genlock really does bring precision timing to software workflows, but only when needed. For most users, NDI's native flexibility is more than enough.